It is 9:50 now. We are commencing today's event with an introduction to the lecture. Please welcome to the stage Professor Chong Shuo Liao from College of Electrical Engineering and Computer Science to give a brief introduction to the topic today and help us learn more about
it. So, 我会尝试用双声道这样子哈，因为我们开场，所以大家可以 take it easy 这样。好，那这个简单的来说，这个 Robert Tarjan 教授应该大家都在 textbook 有看过他非常多的这个杰出的结果哈。那因为在这个Turing Award 的 ACN 的这个 clip 里面，这个 channel 里面呢有一个很有趣的影片，那我特别挑出来，是他当年还是学生的时候。在这个找寻指导教授的过程中，都有一些分享这样，所以我想这个是特别有趣的影片，所以我特别挑这个6分钟的影片来提供，这样等一下可以让大家看一下，这个不管是在学习还是说在做研究的过程里面，可能有一些这个相对于你要怎么去走你人生的第一个问题的时候，的一些启发这样子。好，I just want to introduce the Professor Tarjan's. I think he got many clips on the ACN Turing Award channel. So I picked one. I think that one is quite inspired because the film talk about when he was a student, how to look for his first problem for his research. So I think that's quite good. So welcome to join the introduction film session. Okay? Yeah, please.
When I got to Stanford, I was interested in automata theory, but Stanford had John McCarthy and Ed Feigenbaum, these gods of artificial intelligence. So I kind of thought I would maybe do artificial intelligence. But what I was really thinking about was more complexity, computability. I remember a conversation with Michael Arbib my first year at Stanford. He was in the EE department, not in the computer science department. He said, don't do automata theory, do complexity. So I started thinking about other stuff, and I took some classes, and I decided that at that point artificial intelligence was too fuzzy. It wasn't mathematical enough. And I took a class with Bob Floyd, which was all about problem solving, algorithmic problem solving. So in my first year, I pretty much passed all the requirements needed for the PhD except actually doing the research and writing the thesis. So that kind of set me up for the next step. And I talked to Don at that point. I mean, Don at Stanford was another god by that time. I mean, he became very important very fast in the field. Talked to him about taking me as a student once I decided I didn't want to do artificial intelligence. But he had a policy of taking 2 students every other year. So I was in the off year. So I ended up not as my advisor. Eventually Bob Floyd became my advisor. But after my first year in grad school, John Hopcroft came on sabbatical. So I think he came in the summer after my first year in grad school when I was all set to start doing research because I'd finished all the requirements. So then we started talking about algorithms and algorithmic problems and so on. And we ended up sharing an office, as I recall, and we started working on graph search. And with the mathematics, he was an engineer, so he took a very engineering problem-solving perspective. But I was trained as a mathematician, so I wanted to sort of develop a theory. What is graph search? What is depth-first search? What can you do with it? What does it do to a graph? Anyway, between the two of us, we eventually, we started out by using depth-first search to find bi-connected components. And then I took this idea and went back to the planarity testing problem. and worked on planarity testing for a year. We started out with we were trying to get a fast algorithm. We knew that the Lemp-Lev and Cederbaum algorithm took quadratic time in the number of vertices. I found another technique which was, I'm not sure who developed it first. I think Shirey at Wisconsin, but the idea was to find a cycle and then remove the cycle from the graph and look at the connected pieces and figure out how to embed the connected pieces either on the inside of the cycle or on the outside of the cycle so it all fits together and is consistent. There's a natural recursive structure that you get out of this, and we were trying to find a way to implement this algorithm using depth first search. So we played around with it. We got a rather complicated algorithm that ran in order n log n time, but there was no reason to believe it couldn't be done in linear time, so I spent most of a year dreaming a lot about ways to try to make this thing work in linear time, and eventually managed to solve it. So that turned into my PhD thesis. So I kind of raced through grad schools, as it turns out, but it was a great time to be doing algorithms because there were all kinds of unsolved problems. And this idea of Knuth had developed the idea of analysis of algorithms, concrete analysis of algorithms, but he paid attention to constant factors. And John and I decided that if we want machine independence, we should ignore constant factors. And this turned out to be a very powerful idea.
Absolutely. And my recollection of first being exposed to Knuth's work was in the context of analyzing not just algorithms, but really programs. And so the constant factors were the issues.
And sometimes not even constant factors, sometimes additive factors.
Yes.
We weren't doing things like sorting problems. We were doing things somewhat more abstract. I mean, dealing with graph algorithms. So, and we were worried about the order of magnitude of growth, the asymptotics, and it just seemed like if you ignore the constant factors, just worry about the growth rate. If you think about it, you want to solve big problems. So as the problem grows, the asymptotics become more and more important. The constant factors become less and less important. And if you can abstract away the constant factors, you save yourself a lot of grief. So it's kind of a first cut, but it's a very important first cut.
Good morning, distinguished guests. Welcome to NTU Royal Palm Lecture Series. To begin the event, please welcome Professor Zonglin Wu, Dean of College of Electrical Engineering and Computer Science, to open the lecture.
Our distinguished guests, Professors Robert Tarjan and Professors Cliff Stein, and also our respected academician, Dr. D.T. Lee, 李德才院士, and also our NTU colleagues, students, and all our industry partners. Good morning. It's truly our honor that we invite the Professors Robert Tarjan and Professor Stein to visit National Taiwan University. And Professor Tarjan will give us a speech. And Professor Tarjan is the 1986 Turing Award laureate, and also the distinguished university professors of computer science in Princeton University. His work, ranging from the planar graph theory to the elegant and powerful data structures, has profoundly shaped the modern computing with real applications, including the semiconductor and the integrated circuit design. So Professor Tarjan today will guide us through a journey ranging from his long-term research about data structures to his latest breakthrough about the shortest path algorithm. I believe that we can enjoy and inspire by his talk and learn how to transfer the fundamental theory to an outstanding innovations. But because I am not exactly in the field of computer science, so I would like to invite Dr. D.T. Lee, who is the old friend, long-term friend of the Bob, and give him more detailed introduction. Let's give a warm applause to Dr. Lee.
Good morning, everyone. Good morning, Dean, ladies and gentlemen. It is really my greatest honor and pleasure, my personal privilege, to introduce our distinguished speaker today, Professor Robert Tarjan. Bob and I have been longtime friends for many years. It is always a pleasure to welcome you back to Taiwan again. And Bob Tarjan is currently the James Smith McDonnell Distinguished University Professor of Computer Science at Princeton University. He earned his bachelor degree in mathematics from Caltech and a master's and PhD degree in computer science from Stanford University, completing his dissertation in 1972 on efficient algorithms, efficient planarity algorithms under the supervision of our late computer scientist, well-known Robert Floyd. Over a distinguished career spanning decades, Bob has made pioneering contributions that shaped much of the modern theoretical computer science. He introduced efficient algorithms, graph theoretical algorithms, particularly his development of depth-first search and the strongly connected components algorithms, which revolutionized the field of computational graph theory, and co-invented powerful data structures such as Fibonacci heap and the splay tree. He was the first to rigorously analyze the union find or disjoint set data structure, showing that with techniques of a union by rank and the path compression, one can achieve a nearly constant or inverse amortized time per operation, a result that remains optimal today. Because of these and other contributions, many other contributions, he has been widely honored. He received the ACM Turing Award in 1986, jointly with John Hopcroft, for fundamental achievements in the design and analysis of algorithms and data structures. He was the first winner of the Rolf Nevanlinna Prize, now the International Mathematical Union, IMU, Abacus Medal in 1982, recognizing his deep mathematical accomplishments in information science. Recently in March, he received the 2025 Basic Science Lifetime Achievement Award from the International Congress of Basic Science for his outstanding and innovative contributions to computer science, mathematics, and physics. He is a member of major scientific academies, including the US National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences, among others. What impressed me the most, beyond the brilliance of his algorithmic theorems, is his enduring curiosity and the breadth. Over the years, his work has ranged from the pure theoretical breakthroughs to data structures and algorithms that underpin real-world systems and influence everything from networking, network optimization to compiler design. Even now, his research continues to push forward the boundaries of what we know about graph algorithms, network flows, and the computational complexity. Ladies and gentlemen, Professor Tarjan is not only a titan of theoretical computer science, he's also a generous mentor, a colleague, cherished by many, and a lifelong friend to those who have had the honor to work with him. With that, it is my great pleasure to invite Professor Robert Tarjan to the podium to deliver his distinguished lecture entitled, Is Dijkstra's Algorithm Optimal? Let's welcome Professor Tarjan.
Thank you, Dr. Lee, DT, who invited me here, and to all the people at NTU who helped make this possible. I never get this kind of audience in the U.S. It's kind of interesting, but I appreciate all of you for showing up. This is the second time I've been in Taiwan. It's a lovely country, and next time I'm going to bring my wife and spend longer time and do some sightseeing. I'd like to talk to you today about this question, is Dijkstra's algorithm optimal? And it'll indicate some of the themes of my research over time. So probably I could be the grandfather of many of you in this room. I've been doing this since 1972 when I got my PhD. That's a very long time. So I think I've earned the right to make a few philosophical observations. So let me start out with that, and then we'll get into the substance of the talk. So computer science, unlike mathematics and physics, even though I view it as a branch of mathematics, is a very young field. It's only been around as a discipline since the end of World War II, if one wants to be generous, with some exceptions, notably work of people like Alan Turing and logicians starting in the 1930s, and even Babbage in the previous century. So we've developed many beautiful and theoretically efficient algorithms and data structures, but it's still a young field. The fact that it's a young field means that we've often settled for the first good enough solution. We've sometimes strived for theoretical efficiency at the cost of simplicity. We haven't fully explored the design space for possible algorithms and analyses. So what does this mean? In the design space, if we're designing algorithms, the faster computers get and the bigger memory sizes get and the more processors we have, the more possibilities we have to design algorithms. So I want to suggest, and my personal research goal over time has evolved to be this one, to try to develop and analyze what we can think of as reference algorithms. Paul Erdos, who was a famous mathematician, had this concept of proofs from the book. This is the book in the sky, God's book of proofs. We can think of algorithms in the same way. We want the best possible algorithms found by systematically exploring the design space, algorithms that are as simple as possible, with provable resource bounds for important input classes, and that are efficient in practice. If an algorithm is not simple, no one is going to try to implement it and use it in practice. And of course, if it's not efficient in practice, no one is going to use it. Einstein, this is a quote that was attributed to Einstein, something like, make everything as simple as possible, but not simpler. Be careful about oversimplification. So these are general ideas, but when we think about computation, there's an important notion, and that is the one of data structures. Turns out that the key to solving many combinatorial problems and other sorts of problems is to represent the information associated with the problem so that we can do certain simple operations on that information efficiently. Queries, that is, ask questions about the data and updates to the data. And often we see that, say, a graph problem becomes really a problem about data structure. So the key to solving the problem is to choose the right data structure and implement the data structure in the right way. Now, data structure, we're doing a sequence of very simple operations, queries and updates. We don't really care about the cost of each individual query and update. We only care about the total cost of the entire sequence of operations on the data structure. And this led various people, notably Danny Sleator and me, to analyze data structures not from the worst case per operation point of view, but from the amortized time point of view. I didn't put a slide in here about this, but this is an important idea because it enriches the design space for data structures. We don't care if an individual operation is expensive as long as the long sequence of operations is expensive. And this idea of amortized efficiency plays a huge role in design and analysis of data structures. We'll see a couple of examples of it. So let's take a look at this shortest path problem, which is the main subject of my talk here. This is a classic problem from network optimization. We're given a graph, a directed graph, so we have a set of arcs connecting vertices, and the arcs have a direction to them, and they have a length. And we're interested for a given start vertex or source vertex of computing a shortest path from the start vertex to every other reachable vertex, or perhaps to some subset of the vertices, or perhaps just to a single one. This is the routing problem in your favorite mapping app, be it Google Maps or what have you. And of course, today, this problem on road networks can be solved incredibly fast using the special structure of the graphs that correspond to road networks, and also using some of these basic ideas that appear in Dijkstra's algorithm that I'm about to get to. All right, so every arc has a length, and we're interested in the sum of the arc lengths. That's the measure of the length of a path, and I'll denote the length of an arc from V to W by C of VW. So here's an example graph. We're interested in paths from the source vertex S. We assume the arc lengths are non-negative. That's critical in making this algorithm correct, Dijkstra's algorithm. There are other algorithms that handle a situation where there are negative arc lengths. So Dijkstra's algorithm is a sort of obvious greedy strategy for finding shortest paths. We maintain for each vertex the length of the shortest path to it from S found so far, which is initially 0 for the start vertex S and infinity, or some large value for every other vertex. And then we gradually update the distances as we find better paths. So the distance of a vertex is always decreasing until it gets to the minimum value, which is the length of the shortest path. To do the updating, we maintain a set L of labeled vertices. I'll call them labeled vertices. This is standard. These are vertices for which we have found some path from S, but we don't know yet that this is the best possible path. So initially, S is in the labeled set because we can't get to S. We're at S, cost 0. There are no negative edges. We can't have a shorter path. Every other vertex is not in the labeled set because we don't have any path to it yet. And here is the algorithm. It's a simple loop. We repeat until the labeled set is empty. Delete from the labeled set some vertex that has minimum distance, minimum current distance d of v. We are guaranteed, and this has to be proved, that this vertex v, we now have the minimum possible length to that vertex. Having removed that vertex from the labeled set, we do what I call a scan operation, which updates other vertices distances based upon arcs from V. So if we know the shortest path to V, and for every arc from V out to another vertex W, we have a path which is the length of the path to V plus the length of the VW arc. We compare that to the current value of D of W, and if we get a better value, we do the corresponding improvement. So there are two possible ways this can happen. If this vertex W is unlabeled, that is, it has an infinite value, then we know we've got the first path to W. We set D of W appropriately, and we add W to the labeled set because we now have a path to it. But another possibility is that we already have some path to W, but we've now found a better path, and we do the appropriate update, which is to decrease the value of D of V. We set it to the new value. So that's the entire algorithm. Now what is missing here is that we need to maintain this set L. But before we discuss how we do that, let's just look at this example graph. So initially, S, the start vertex, is the only labeled vertex, so we remove it from the set S. We know its distance to itself, and we scan S, which is going to give us a path to A of length 5, because we have this SA edge, and a path to C of length 6. So after the scan of S, the picture looks like this. A and C are now labeled. S is finished. And the next vertex to be scanned is A because its distance, its current distance, is less than the distance to C. So we know now that A has shortest distance, 5. We scan A. We've got two outgoing arcs to B and to D, so we get a path to D of length 14 and a path to B of length 19, and they both go in the labeled set. And now C is the vertex with the smallest distance label, so we scan it, and now something new happens because when we scan C, we've got this arc from C to D, and we've got the length of the SC path, which is 6 plus 6, which is 12, which is better than the current value to D. So now we need to update the distance to D. It decreases from 14 to 12. So after this, and we also get F as a new labeled vertex. So after the scan of C, this is the picture, and I think I'll go one more step here. So now D is decreased, but F went in with 10 because 6 plus 4 is 10. So now we scan F, and this gives us a third path to D and also a new path to G. So D again has its value decreased to 6 plus 4 plus 0, which is 10, which is less than the old value of 12. So after the scan of F, we get to this picture, and the next vertex to be scanned finally is D. And you notice that D went through 3 distances, 14, 12, and 10, and this is in general what happens. Now this algorithm was described in a paper by Dijkstra published in about 1960-ish. He actually did not invent the algorithm. This is an example of this happens a lot in mathematics. Someone's name gets attached to a theorem, but they didn't actually discover or prove the theorem somehow. So Dijkstra described this paper this algorithm in a beautiful short paper, and his name is now associated with it forever. He also described a minimum spanning tree algorithm that works in a similar fashion, which was also discovered by several other people before then. In any case, it's straightforward to prove that the algorithm is correct. What we need to prove is that when a vertex is scanned, its current distance is its correct minimum distance. And importantly, this follows because the vertices are scanned in non-decreasing order. That is, they're scanned, not labeled, scanned in increasing order of their distance from S. So if we're only, let's say you have a car, electric or gas, doesn't matter, and you want to find the set of vertices you can reach with your current amount of fuel or charge. You can run this algorithm until you scan a vertex that requires more fuel or charge than you have in your tank or battery and stop at that point because it's producing the vertices in the order of cost. I'll call this the distance order problem. Produce the vertices in the order, sorted order by their distance from S. This is a harder problem in general than just computing all the distances because we have to produce them in sorted order. And the algorithm builds a shortest path tree which realizes a set of shortest paths from S to all the other vertices. And I illustrated that in the picture with the blue arcs, which are the shortest path tree that's getting constructed. Good, so what about efficiency? Now we get to this situation that I mentioned. This is an example where we go from a graph problem to a data structure. If we represent the graph by, for each vertex, having a list of the outgoing arcs, then most of the work, except for processing the labeled set, is linear in the total graph size. So we get linear time plus the time to process the labeled set. So this is the restatement of the algorithm, and let's look at what's happening with the labeled set. The first step is we delete from L some vertex with minimum distance. I'll call that a delete min operation. Within the scan loop, if a vertex is unlabeled, we have to insert it into the labeled set with a given distance. And if it's labeled and we get an improvement, we have to decrease its distance. I'll call that a decrease key operation. So now we've got a data structure problem. We want to represent a set, each element of which has an associated value, non-negative, real number. We want to be able to do insertions into the set with initial values. We want to be able to delete an element with minimum value, minimum key, and we want to be able to decrease the key of an element. And if we can implement all these operations, we get an implementation of Dijkstra's algorithm. There's one delete min and one insert at most for each vertex, and there's at most one decrease key operation for each arc. So on a graph with n vertices and m arcs, this algorithm takes linear time, order n plus m time, plus the time for at most n inserts into the labeled set, at most n delete mins, and at most m decrease keys. So now we need a data structure that efficiently supports these three operations. And we don't care about the time of an individual operation, we only care about the total time of all the operations. I'll call such a data structure that supports these three operations a heap. It's also been called a priority queue. Knuth called these data structures priority queues. A heap started out as a special kind of priority queue implementation. I prefer using heap for any implementation that satisfies the requirements here. So what's the history of heap implementations? Well, Dijkstra ignored the data structure question. He represented the heap by an array indexed by vertex with the key stored in the array slot. So this makes insertion and decrease key constant time operations because you just stick the current value in the array in the right place. But to do a delete min, you have to scan the entire array and find a minimum value in the array. So the delete mins are the dominant part of the algorithm here. The running time is order n squared, where n is the number of vertices. This is best possible on a complete graph, a graph that has all possible arcs in it. But that's not really the most interesting case, because if you look at a road network or any current real-world network on which you want to run shortest path computations, it tends to be very large and very sparse, constant number of arcs per vertex. And then this bound is quadratic in the graph size, so one can conceivably do better. Williams, in 1964, building on a paper by Bob Floyd, who was my thesis advisor at Stanford. Just a side note, Stanford was an amazing place to be a grad student in the late 1960s, early 1970s. I had the extraordinary luck to have 3 Turing Award winners on my thesis committee. John Hopcroft, who was visiting from Cornell, Bob Floyd, my advisor, and Don Knuth. So it was a very special time and place, and I was extremely lucky to be there at the time. In any case, Floyd and Williams were interested in sorting, and they devised a data structure, which is a binary tree of vertices heap ordered by key. We don't need to worry about the details. The important thing is that delete min only takes log time in this data structure. The cost is that the time for insertions and decreased keys also increases from constant in Dijkstra's implementation to log n. So the result is that the running time for Dijkstra's algorithm, if it's implemented using one of these data structures, is m, the number of arcs, times log n, times some constant. And this implementation still, as far as I know, is best in practice, but not with a binary tree, with a 4-way heap-ordered tree stored in an array. And the reason this works so well, even though we can do better theoretically, is that there are no pointers in this data structure. You can navigate through the binary tree using address arithmetic. Now this was the state of the art until 23 years later when I worked with Mike Fridman on this problem. We realized that we could improve this running time if we could reduce the time for the decreased key operations, which are the dominant. We're doing m, number of arcs, decreased key operations, but only n insertions and n delete mins. Now we can sort with the heap data structure, which means we can't do better than n log n time, because we can insert n items and then repeatedly delete, and that sorts the n items, and there's a classic lower bound for sorting using binary comparisons of n log n. But this m log n bound, if m is large compared to n, this is bigger than n log n and grows with the ratio of m to n. So we tried to design a heap implementation that would take constant time for decreased key, constant time for insert, and only log time for delete min. And we were able to do this using this notion of amortization, which is to say that the time of a sequence of heap operations is some constant times the number of insertions, plus a constant times the number of decreased key operations, plus log n times the number of delete min operations. And that gives us this bound for Dijkstra's algorithm, which is m plus n log n, which is best possible at least for certain kinds of graphs. And this was regarded as kind of the state of the art. But what do we mean here by optimality? That's the question I want to look at today. And I should say that over 60 years, we've developed some beautiful algorithms, data structures, but there are still open questions, unexplored directions. And this work that I'm now about to talk about is very recent. This is the last 2 or 3 years. So optimality. In the worst case, we have to look at every arc. So we have to spend order m time. That means, in particular, as I already mentioned, that Dijkstra's algorithm is optimal on dense graphs. Now, let's look at the distance order. I want to focus on the distance order problem. Again, that is the problem of producing the vertices in sorted order by distance from the source vertex. There's some kind of sorting problem built into this. One can construct graphs on which you have to sort the vertices by distance. A simple example is just a single start vertex with direct arcs to every other vertex in the graph. If we want to get the vertices out in distance order, we have to sort the arcs by length. So we have to spend n log n time based on that argument. That tells us that Dijkstra's algorithm implemented with a Fibonacci heap is optimal on many graphs, certain sparse graphs, and dense graphs as well by the fact that you have to look at every arc. But let's focus not on the general case, but on some specific case. The question we want to ask is, suppose somebody hands us a particular graph. There's some road network, and it doesn't change very fast over time, because to change the road network, maybe there's a traffic accident, so it changes rapidly in that case. But that's going to delete an arc or equivalently change the distance to infinity. But let's suppose we have the fixed road network and we don't know the travel times. Travel times shift over the day. Can we design a customized algorithm for that particular graph that is optimal? Maybe we can, maybe we can't. Is there some algorithm that is optimal for every possible graph? That is, it does as well as every customized algorithm on every particular graph. That's the question I want to take a look at. So this is the notion. My co-authors call this universal optimality. This is a little bit highfalutin, but it's related to instance optimality. So we're given a fixed graph. There's some best possible algorithm. Fixed graph, unknown arc lengths. Is there a simple algorithm that is as good as the customized algorithm on every single possible graph? That's the question I want to address. And the answer, it turns out, is yes. In particular, an extension of Dijkstra's algorithm that uses the right kind of heap implementation has this universally optimum property. That is, even if I hand you the graph and you are allowed to design your own customized algorithm for this particular graph, you can't beat this improvement of Dijkstra's algorithm by more than a constant factor in either running time or number of comparisons, which are the two useful measures of complexity in this setting. Now, to illustrate this idea, let's look at this example. This is a long path plus k vertices off to the side with direct arcs from the source. The top, that node is the source node. So we got the long path here and then all of these vertices. Now we can compute distances from S to everything on the long path with no comparisons. We just add up the lengths of the arcs here. Indeed, if we're just interested in shortest distances, there's only one path to every vertex. This is a tree. So we can compute shortest distances without doing any comparisons. But if we want distances in increasing order, then we have to do more work. If we run Dijkstra's algorithm on this example, what happens? We scan the start vertex. That puts this vertex and all of these vertices into the heap. That's roughly k vertices, k plus 1. And now let's suppose that these arcs are all real short, so the total length here is less than the length of any of these individual arcs. Then what's going to happen is this vertex will be scanned next, removed from the heap. This one will get added, scan, removed from the heap, and so on down the line. The size of the heap is essentially k, maybe exactly k. So we're doing essentially n delete mins on heaps of size k. So Dijkstra's algorithm runs in m, which is the same as n here, n log k time. But there's a better way to do this if k is relatively small. We just sort all of these vertices by the length of these arcs. That gives us the relative order of these vertices. And now we have two lists, and we just merge the two lists together. We compute distances here, and we've got the distances by sorting here, and then we just merge. And merging two lists takes linear time, merging two lists by distance. And the sorting problem takes k log k time. So if we use a Fibonacci, so we can solve the problem in m plus k log k time, which is necessary because the distance order problem, we have to sort the distances to these two vertices, and we have to look at all the arc lengths. So m plus k log k is a lower bound, and we can achieve it, but not with Dijkstra's algorithm as I have just described it, depending upon the values of n and k. So there's something interesting going on here. I already said all of this. So here's an interesting observation. If we go back to this example, what happens when we run Dijkstra's algorithm here? We insert all of these vertices into the heap. And then in the bad situation where the distances to all of these vertices are smaller than all of the arc lengths here, these go out and the next one comes in, out, in, out, in. These vertices just sit in the heap and clog up the works, if you will. We're spending log k time per delete min on these vertices in spite of the fact that these are not doing anything. Now, if we had a heap that that somehow was biased in favor of recently inserted elements, this problem might go away. That's the observation here. Dijkstra inserts the vertices on the long path into the heap after all the k vertices that have direct arcs from S. So this suggests what we can call a beyond worst case or some kind of biased heap structure. We need a heap implementation where the running time is parameterized on some finer grain than just the number of items that happen to be in the heap. We want the heap to give preference to recently inserted items. So this is a vague notion, but we can quantify this in the following way. We'll define the working set of an item X. So X goes into the heap at some later time, it's removed from the heap. We look at that interval. We count up the number of insertions that take place during that period of time. That set of insertions, that set is the working set of this element X, and that includes X itself. So the working set of X includes X, everything inserted after X up to the time X is deleted. The log of the working set size, that's our measure of efficiency for a delete min operation. We'll say a heap has the working set bound if the amortized time, again we have this notion of amortization which is critical here. If the amortized time per insert and decrease key is constant, but the amortized time for delete min of X is log of the working set size. Turns out this can be bigger or smaller than the size of the heap when X is actually deleted, as you can see by examples. In any case, here is the notion. So if we are brave, which my co-authors were, they conjectured that if you use a heap with the working set bound in Dijkstra's algorithm, you get this universal optimality property, and that there actually is a universally optimal, a heap that has the working set bound. These are the two questions. Is Dijkstra's algorithm using a heap with the working set bound universally optimal? And if so, is there a heap that has the working set bound? And if the answer is yes to both questions, then we get a version of Dijkstra's algorithm that is not only optimal in the worst case, but is optimal on any possible graph structure as compared to any algorithm specifically customized for that particular graph. So let me say a few words about why these results hold. So here's the theorem. Yes, on any graph, Dijkstra's algorithm using a heap with the working set bound is universally optimal in running time. It runs within a constant factor of best possible. And if you're counting comparisons, you're within a linear term. And I'll come back to this, linear term in the number of vertices. I'll come back to this question at the end if I have time. All right, so let me just suggest to you how this proof would go, and I won't prove anything, but there's a useful concept here. So how are we going to get a lower bound for a particular graph? There's some kind of sorting problem embedded here. Remember, we're looking at the distance order problem, which is we want to produce the vertices in increasing order by distance from the source. So this is a search order is an order of the vertices. The definition of search order has nothing to do with the arc lengths, only with the graph structure. This is a total order of the vertices such that the start vertex is ordered first, and every other vertex has an incoming arc from a previous vertex in the order. I call this a search order because these are the possible orders you could get by starting at S and running any kind of a graph search from S. The general step is you add a vertex that has an arc from a previous vertex. So all possible orders generated by graph search are the search orders. So it turns out that a search order is a distance order, and vice versa. Every vertex order is a search order if and only if there's some set of non-negative, indeed positive, arc lengths such that the order is the unique distance order for the given arc lengths. So the number of search orders is the same as the number of outputs for the possible graph when you look at all possible arc weights. This means that in terms of number of comparisons, you can apply the sorting lower bound. In order to solve the distance order problem, you have to identify the unique distance order. So if D is the number of distance orders, same as the number of search orders, you have to do log D binary comparisons of sums of arc lengths in order to solve the distance order problem. So this gives us two lower bounds that are specific to the graph. We have to look at all the arcs, and we have to do a number of comparisons, which is at least log of the number of possible search orders of the graph. So again, lower bound is some constant times the number of arcs plus log D. Now here's the interesting result. You can tie this log D to the sum of the working set, the logs of the working sets when you run Dijkstra's algorithm with a heap. That is to say, given a run of Dijkstra's algorithm, if you sum the log of the working set sizes of all of the vertex deletions, that's at most a constant times log D. And this is the interesting proof. My co-authors had this is not straightforward, but it's not real hard to prove. My co-authors had an ad hoc way to prove this, but there's a beautiful, simple proof that is based on a lemma by this set of co-authors, which was reformulated by these folks very recently. And I'll refer you to the paper if you're interested in the details of the proof. So this means that on any graph, Dijkstra's algorithm, using a heap with the working set bound, if there is such a thing, is universally optimum in running time, and it's within an additive O of n term of being universally optimum in comparisons. And you can think of this as order 1 per insertion. Whether you regard this as important or not, this is where things get technical. But let's defer this for the moment. First, we have to ask the question, is there a heap with the working set bound? Now, this is where things get interesting. You know, mathematics has the characteristic that some result will get discovered and there's no application for it. And later on, much later on sometimes, it turns out to have an amazing application. So there is a self-adjusting kind of heap data structure called the pairing heap, which was invented by some of my colleagues and me, same Mike Friedman who invented Fibonacci heaps along with me. We were trying to get a simplification of Fibonacci heaps because they're not so efficient in practice, even though it has nice resource bounds. It turns out that, this data structure has the working set bound under certain restricted circumstances, specifically if there are no decreased key operations and the heap ends up empty. And this was proved by John Iacono in the year 2000. He was a student of Mike Friedman's at Rutgers. He proved this result. He had no applications for it, and his definition of working set was a little more complicated than the one I've given here. So this result kind of sat for 25 years with no applications, but it's almost what we need, except for this issue with the decreased key operations. And there's also this technical constraint about the heap ending empty. We can get rid of that one by slightly modifying the pairing heap data structure. This is a recent result. In any case, this suggests that there should be a heap that has the working set bound along with, and it handles decreased key operations. This is the trouble. So we almost got to use an existing data structure with the existing proof by John, but turns out not. So instead, we invented a new data structure based upon Fibonacci heaps, which do take constant time for decreased key operations, which has the full working set bound. And the idea is that we want to give preference to recently inserted items. So we want to maintain 2 orders on the heap. We've got the order by key. We want to be able to get fast access to the item of smallest key. And we also want to keep the items ordered by insertion time somehow, but this only needs to be rough. And we have the Fibonacci heap, which has constant time decreased key operations. So our data structure consists of not one, but a sequence of Fibonacci heaps, illustrated by this picture, that are in increasing order by size. And the inserts are the most recently inserted items are in the leftmost heap, the small one, and older items are in successively larger heaps that are later in the sequence here. And the numbers work out so that the size of these heaps can grow doubly exponentially in the number of items in the heap. So we end up having order log n heaps if there are n total items in all the heaps. And we do the operations individually on these Fibonacci heaps, which I've denoted abstractly by triangles. And then we're confronted with 2 problems. To maintain the correct growth in sizes of these things, we occasionally have to put 2 of them together. Where did we go here? We occasionally have to put 2 of them together, which is a meld operation. And when we do that, we have to keep track of which vertex is in which heap. That turns out to be an instance of the classic, well, I'm getting ahead of myself. We'll answer this question in a minute. So that's the first extra data structure problem that comes up here. And you see that we started with a single data structure, the heap with the working set bound, but to get to it, we're going to use various other data structures for other problems, and they're serving a secondary role here, but there are applications in which they have a primary role of their own. Now there's a second sort of more obvious thing we have to do, which is that our items are stored in a collection of heaps. We have to be able to, when we want to delete the minimum, it's going to come from one of these, but we don't know which one. So we have to keep track of the globally minimum item. We have the minimum item in each individual heap, of which there are log n, but we have to keep track of the global minimum. So these are the final two pieces of the puzzle to get this whole thing to work, to give us what we need. So as I started to mention, to support the melding, this turns out to be just the union find problem, which you can solve in inverse Ackermann function time, as DT already mentioned, but it turns out it's a special case. You can solve it in constant time because of the sizes of the individual Fibonacci heaps. So this problem we solve using the disjoint set union data structure. And then to keep track of the global minimum, we can either do it recursively, that is, we can build another heap data structure on top of all the minima of the individual heaps, and then you get some kind of log star solution. But since the number of these heaps is very small, doubly logarithmic, there's an array-based solution which directly gives us constant time per delete min for that extra step. So we put all of these ideas together and we get what we need. We get a heap with the working set bound with constant time, decreased key, which shows us that Dijkstra's algorithm with this heap implementation is universally optimum, at least with respect to running time. Now let me say a few words about this comparison-based issue. It's illustrated by this example again. If we go back to this example, how many comparisons do we actually need to solve the sorting problem? I gave you an algorithm. So Dijkstra's algorithm runs in n log k time on this example. There is an algorithm that runs in n plus k log k time, where k is the number of nodes on the bottom here. And n plus k log k time is optimum in time because we have to look at all the arcs, of which there are n minus 1. But we don't have to do that many comparisons because there are no comparisons required to compute path lengths along this path here. The problem we need to solve is we need to sort the k vertices by the length of the arcs. That's k log k time, and then we have to do this merge problem. Merge the distances for these vertices into the distances for the vertices along the long path. The classic merging algorithm just takes the first two items, compares them, that gives the first one, the next two items, compares them, and so on. It takes linear time. But there's an optimal merging algorithm that takes the first one, does a binary search into the long path to find the right place to put it, takes the next one, does a binary search, and so on. Let me back up a bit. The number of search orders of this graph is n choose k, because the number, each of these k vertices can be inserted into this long path in n possible ways, and then this is subject to permutations of these vertices. So it turns out that d, the number of search orders, is n choose k. The log of d is about k times n over k. So if we're going to be optimum in comparisons, on this example, we need to take k log n over k comparisons, which we can do by sorting these vertices and then using an optimal merging algorithm to do the merging step. So again, there is a customized algorithm that does best possible in comparisons, And this merging problem is actually something I worked on with Mark Brown back when I was a faculty member at Stanford. Okay, but this is only for this special case. But indeed, we can solve this problem. We can get rid of the additive linear term in general. And the idea is to use a recursive version of Dijkstra's algorithm. We observe that if there's some vertex, so here's the source vertex, here's some vertex, if getting from the source vertex to some other set of vertices requires going through this vertex in the middle, I'm going to call that a bottleneck. That's not exactly the definition in the slides, but we can think of running a recursive version of Dijkstra's algorithm where we start from the source vertex. When we get to this bottleneck vertex, we restart Dijkstra's algorithm, and that's illustrated in the picture here. So here's the recursive version of Dijkstra's algorithm. We pre-compute somehow a set of bottleneck vertices that block everything from the source. And these bottleneck vertices have a total order which we can discover, and the algorithm is a breadth-first search. And then we run Dijkstra's algorithm with the heap with the working set property. But as soon as we scan one of these pre-identified bottlenecks, we restart Dijkstra. We do a recursive call of Dijkstra. So we got the V1 here in our Dijkstra run from S. Now we do a new Dijkstra with a new heap starting from V1. When we get to a new bottleneck, we call a new Dijkstra and so on. So V3, in this case, we've only got 3 bottlenecks. When we finish the Dijkstra run from V3, we restart the V2 Dijkstra and so on and so forth. By the time we finish the original call, we will have computed all shortest path distances. Now we have to deal with arcs that go from an internal call to an outer call, but this is just a decreased key in the outer call, and we can handle these. The other issue is that this algorithm produces the vertices, the correct distances to vertices, but it doesn't compute them in sorted order. So we have to do something like this optimum merge process that I described to finally produce all the vertices in sorted order. And this gives us an algorithm that is not only universally optimal in time, but universally optimal in comparisons. And the data structure to keep track of the sorted order is something, yet another one of these data structures that was invented for something else called a finger search tree, where we have a binary search tree with fingers into it, and we can access positions near the fingers efficiently. That's also something I worked on with Mark Brown and various other people decades ago. And it's interesting how these classic results feed into new results. So to summarize, recursive Dijkstra using a heap with the working set bound and with the distance order correctly represented is universally optimal in running time and comparisons. And there's actually a different, somewhat less elegant algorithm that actually produces the vertices, scans the vertices in exact distance order. I'll refer you to the paper. This result got Best Paper Award in Fox last year, and there's a complete rewrite which is on arXiv, which for the moment is the reference version of this. So take a look at the arXiv version. I should say that Bernard Hoepler, I did this work with Bernard and his group, which was at ETH in Zurich at the time. He's now at Insight, which is a research institute in Sofia, Bulgaria. He was a master's student, visiting master's student from Munich. He came to Princeton. We spent a year together. Brilliant guy. I reconnected with him in Zurich, and he pulled me into this problem, so I started working on it. Now, I see I'm running a bit over time, but if you'll give me maybe 3 more slides, I have a bit more to say, because so far I've said the answer to this question is yes, but what is the question? Well, the question is, what is an optimum algorithm to compute a distance order? Which maybe we want, but maybe it's too much. So what happens in a situation where we only want the distances, not a distance order? In this case, the answer to the question I asked at the beginning is no, Dijkstra's algorithm is not optimal. There's a beautiful, again, very recent result that gives that m times log to the 2/3 n time deterministic algorithm to compute exact distances and the shortest path tree. So it beats Dijkstra on sparse graphs. This is a result of Ron Duan and several of his colleagues. This was best paper in stock, one of the best papers in stock, 2025. So this is a real breakthrough. And I think it's not necessarily best possible. I think there's more work to be done here. For one thing, log to the 2/3, this is too complicated a bound to be the real answer. So here's a possible place to go. There are still open problems on these classic algorithms. We don't understand everything yet. Now, one more thing, there's a sorting problem here. So here's a related problem, which is a pure sorting problem, which is another classical problem. We know that sorting n items by binary comparisons takes n log n time, because the number of possible permutations is n factorial. A comparison makes a binary decision, so it splits the possible outcomes into two pots. An adversary chooses the direction that leaves the larger set as a set of possible answers. So you have to do log of n factorial comparisons to sort. That's n log n. That's one of the very few lower bounds, non-trivial lower bounds we have for any kind of algorithm, short of things that are super NP complete. But what happens if we're given some comparisons to which we already know the answers? Sorting using partial information. This is a classic problem. Turns out the same techniques we use to solve the Dijkstra problem can be used to give an optimal algorithm for this sorting using partial information. The algorithm is beautifully simple. In this case, there are no decreased key operations, so we can use pairing heaps or double pairing heaps and just plug into a very simple algorithm to get an algorithm that is optimal in both time and comparisons. So John Iacono learned about our Dijkstra results and pointed out this connection to us, and we worked out the details. This is in SOTA 2025, and this is really the more basic result, I would say. So historically, the Dijkstra result came first, but this one is more basic and possibly more important. This one you can find both in the proceedings and on archive, and it just got accepted to Algorithmica. So with that, I will close, and I expect I hope there's time for a few questions, which I'll be happy to answer. So thank you very much.
Thank you, Dr. Tarjan, for your very insightful speech. Okay, we now enter the panel discussion. Please welcome today's panelists, Dr. Robert Tarjan, Dr. Clifford Stein, Professor in Data Science Institute at Columbia University, academician Dr. Decai Li, and the moderator, Professor Chongshuo Liao. Please give them a warm round of applause. And now the floor is open to the audience. So if you have any question, please raise your hand and wait for a microphone to be brought to you. And before putting your answers, please introduce yourself by stating your name and affiliation.
Okay, thank you. Okay, so thank you very much for Professor Tarjan's inspiring talk. So your insight into the evolution of the algorithm and the data structure, especially regarding the graph and the shortest path problem, that's given us much to reflect on, and especially the elegance of the result. that's not only highlight the latest breakthrough, okay, in this field, fundamental field, and also your lifelong commitment to advance in the field, which inspired all of us. So let's move on to the short panel discussion. So before that, I would like very pleased to thank Professor Cliff Stein with Columbia University and academician Dr. DTT to join the conversation. Okay, so Professor Tarjan, yesterday we talked about how quickly AI is changing our daily life, right? So, and crucially, I think how AI is reshaping the way we learn and teach, especially for higher education. So in just the past year, we have seen all the large language model demonstrate the striking capacity, especially in mathematics, reasoning, and even like the formal proofs. So I think it's quite amazing time. But to kick off the session, could you please share your thought on especially how students and faculty members we might best utilize these AI models in teaching, learning, or even research, okay, especially for these fundamental subjects such as data structure and algorithms.
Let me start by asking the audience a question. How many of you have used ChatGPT to help you in your classrooms, shall we say, or in your classes? Don't be shy. I think, first of all, this is a huge challenge to us as faculty to figure out how to integrate these systems into our teaching, because obviously you can't ban them from the learning process, but at the same time, and they're a great resource. So how do I use ChatGPT and related systems? At the moment, it's mostly to do searches, to help me with searches, to find references, which is a very powerful and important, but very simple application. I am curious to see how these systems can help in actually solving open problems, doing my professional work. I haven't had a chance yet to investigate this, but I hope to do so soon. But I think getting back to teaching, we really have to figure out, and I don't know what the answer is, and this is going to evolve over time, but I think it's going to change the way the educational process works. On the one hand, many of my colleagues think this is going to lead to less homework and more in-class limited resource exams, because it's very important. So these systems for you as students are maybe an easy way to do certain kinds of problems. But remember what you're in school for. It's to learn how to think. So if you're going to use these systems, everybody's under time pressure, yes, but remember what you're in school for. It's not necessarily to get great grades. Nobody will care about your grades when you're out there in the real world. It's to learn how to think and to improve yourself as a human being. So keep that in mind. Find ways to use these systems to help you improve your learning and your expertise. That's my advice to you. And trust but verify. These systems make mistakes. They hallucinate. They're getting better, but they do not operate the way human brains work. For one thing, they're way less efficient. They take many more examples. There's something we don't understand. I'm not a believer that the so-called singularity is going to arrive anytime soon, but these technologies are still very powerful. I think in terms of teaching, this could go in several directions. One is less homework, more in-class exams. What I have tried to do so far is to design problems that these systems cannot solve, which is an ongoing and interesting challenge. Maybe Cliff has a response.
Yeah, thanks. So Cliff, how about, yeah.
Hi. So thank you for inviting me here today, first of all. I will try to expand. I mean, I agree with what you said, and maybe to expand on it. The idea that you want to use, right, it doesn't make sense not to use them because everyone uses them and they're going to be part of the world going forward. But to use them in a way that actually furthers, your education, and you have to take some responsibility for that. So if you're, if it was a problem where you had to design a new algorithm, perhaps, and implement it, then it does make sense to use some of these tools to, put the scaffolding of your code together. If you were using a heap, which, people know how to do, it doesn't really make sense that you have to sit there and write a heap at this point in your life if you've done it once, so to use the tools for things like that. But at some point, you want to learn how to design an algorithm, you want to learn how to analyze it, and that you should be doing yourself. And it's exactly if you don't, then you may get it right this time, and you may fool the grader this time, but then you haven't learned the skill. And as Professor Tarjan said, these things do hallucinate, and the only way we can ever use them, now you're in a real situation years from now, and you're working in a medical situation, and you're designing tools to use it, and they better be right? And the only way that you can do that is to have be able to do it yourself and be using the tools to speed things up or to aid them along. And so it's very important in the educational process to do it in that way, that you are actually doing the learning yourself. And of course, the problem is that people want to get good grades, and maybe that isn't the path to the best grade, even if it is the path to education. So I think, as students, you have to take this responsibility for your own education, or else the system is just, not going to work. And there's no reason it shouldn't be that way. And I'll just say also, for research, there's, again, using it for search and using it to test ideas. There's a paper on arXiv recently by people who use ChatGPT for science research that I encouraged. It came out a few weeks ago. I don't have the exact title, but I encourage people to look for that and read it as a really good example of ways that these can be used, and ways, the pitfalls also.
Thanks. Yeah, so yesterday also Professor Sullivan, he also mentioned that the critical step is that we need to know how to verify the correctness, and to check all the correctness, especially from those LLM models. So I think,
Yeah, it is very important that you know what you get, because when you write a code or write a program, you put it in a computer, and the computer give you output, right? Whatever you give them, computer always give you output. Just like when you ask questions to ChatGPT, they'll give you something. But the question is whether or not that something you get is related or relevant to what you ask, is related to what you ask. So I think I agree with Professor Tarjan. You have to know to verify what it is. But the question is, do you have the knowledge in verifying whether or not the ChatGPT gives you is correct? So I'm really worried in the sense that if people like you, I think you work and you know what it is, how you judge or evaluate the output. But the question is for those teenagers, when they do not have any prior knowledge of it and using it without any guidance, that could spell disaster. But the question right now, I think here is that when you are, I pretty agree with Professor Tarjan that you are here in school, you are learning, you try to learn how to think, how to say. So remember, when you are out there, well, of course, when you do this grades, this is what the faculty members here now are most afraid of. The thing is when you give the exams, and then you just turn out answer and report answer back to professors. And the question, professor, how do you grade them, right? Does this make it hard? So you don't know, because this is an offline process, and we as faculty members cannot really know what you produce is what you actually know or what you produce by ChatGPT. So this basically make it hard for us. But the question is this: if you do it in a way without thinking, and it come to really, this is not really what the purpose of it. If you really concerned about the grades, and that's probably would be a problem for you in the future. Because when you graduate out there, go to the society, you work in the market, in the job market, workforce. People ask you questions. You have to be there online. You have to speak, answer, respond online without the tools. So the process is basically you have to learn how to really know the answer. So using GPT, I think I use it also not very often, but then I use it occasionally. The answer that they gave to me is really, really helpful. Really helpful because I need to do something here. I really do not have the time to prepare the background information and ask them and to produce this one here for you. It's very, very nice. So really it saved me a lot of time. So in terms of the efficiency and everything, it's quite useful, to be honest. But then the question is that whether or not you use this tool here in the right way to benefit you, to strengthen your knowledge base, and then to absorb the idea is more important. So we have, here in this, I remember the word that says verify, always verify, and then never trust. This is what we, in the cybersecurity area, it's called zero trust. No, never trust. You always verify because you don't know who you're dealing with. Because in the digital world, you don't know what it is. That's why you never trust. Always verify. That's what they call it. Zero trust principle architect that we use. But when you use this ChatGPT, be careful about it. Thank you.
So thank you very much for sharing your insights. So now we have about 10 to 15 minutes. So I would like to invite our students and faculties to prepare your questions to any of the distinguished panelists. Yep, please.
Hello, Arthur from Mechanical Engineering Department. Thank you, Professor Tarjan, for your very amazing speech. I got a few questions. So when you're inventing or discovering a new method or algorithms, did you have a target, so to say, complexity? For example, you want to decrease log n to maybe order 1 or something, or you just discover, okay, there is a problem, I want to solve it, but I don't know how good can I achieve. And this question can be generalized to a broader sense. Like when we discover a problem, we want to solve it. Do we set a goal? How good I want to achieve, or I just want to improve, but I don't know where exactly I'm going to? Yeah.
That's a very good question. Let me answer it in I'll answer a different question. I like to give my students problems where I don't state the answer, or I state the question in the form, here is a statement, is it true or is it false? Or here's a problem, is there an algorithm with a certain characteristic or not? That is, produce an algorithm or produce a counterexample. And the students don't like this because it's too ambiguous. The research, the most important thing is to ask the right problem. So actually, to get back to your specific question, I think one wants to ask an ambitious question. That is, with the Fibonacci heap, for example, we asked the question, can you get constant time? Not, can you get an improvement? And we managed to succeed in getting constant time for decreased key. We could have failed, but then maybe we would have got some other improvement. I think you want to set some kind of goal which is sort of best possible and then see how far you can get toward the target. Also, it's important to work on both sides because if you're working on the wrong side, you're doomed to failure, right? But if you're working on the wrong side, maybe you get insight into how to, suppose you're working on an algorithm and you come up with some examples where it doesn't work, then maybe that allows you to build some kind of a counterexample. Or maybe you play with bad examples and you figure out how to address those, and then you can use those methods to produce an algorithm. So I think working on both sides of the question, if it's a yes-no kind of question, is very important in solving class problems and doing professional research. Be ambitious. It's easy to be incremental. I mean, I worked on a lot of stuff over time, but in recent years I've kind of concentrated on what I regard as fundamental problems.
Griffin, you want to share something?
I'll just say. Actually, my first research problem came from Professor Tarjan, exactly in the way he described. And yeah, it was a little disconcerting as a student, but in the end it worked out because he was right about what you could do. But I also, just to, like the shortest path, I mean, that's, right, you know what you need because of, right, you need the data structure to get a certain result in the Fibonacci heap. So sometimes, I mean, it happens to also be the best possible, right? So sometimes it is that, I think sometimes it is a situation that tells you what you want too. That's
Great. So any other question?
Hello, I'm Aaron Sidford. I'm a professor at Stanford visiting. Thank you for the wonderful talk. I had 2 technical questions, if you don't mind. So the first one, I thought the notion of instance optimality was very interesting. I was wondering how hard it is to approximate the log of the number of vertex orderings given a graph. And the second question, totally different. I was wondering if you think there is an interesting, good open question to study about maybe all pairs shortest path or multiple source in light of the runtime versus comparison issues that could arise there. But thanks.
I don't have good answers to either one of your questions, so maybe these are good questions for students to take a look at, in fact. Do you have an answer? Oh, okay. I think coming up with the right question is critical in doing good research.
Yeah, thank you very much for the talk. I recall one comment that made my instructor during my algorithm course in graduate school. He said so. The working style or research style of Tarjan is beating something to death. And I witnessed it now. You just want to settle any doubt of Dijkstra's algorithm. It's amazing. But my question is very specific. Okay, is a kind of result from this thing that I discovered a few days ago. I didn't pay attention to this. I was checking what instructor authors recently added to their course or books recently and leave out or take out recently. And I checked Coleman's book. From 3rd edition to 4th edition, they actually took out Fibonacci heaps. You can check.
idiots.
And now my question is, suppose I'm not sure if you are teaching algorithm these days, but what would you take out and what would you add in the age of AI?
I know what I would add, and I wish they had added it previously. So Fibonacci heaps, there are some alternatives. I kind of alternate between teaching Fibonacci heaps and teaching other data structures with the same running time. And Fibonacci heaps are a little bit complicated, so And they also don't get used in practice, so that doesn't trouble me so much. I wish they had put in splay trees. This is a kind of self-adjusting search tree instead of Fibonacci heaps, or I think that's the one thing that they could have added that they didn't. In terms of AI, AI, the kinds of mathematics you need to know are statistics, applied linear algebra, and so on. And Cliff may have a better answer to that question for AI material than I do.
So first of all, Fibonacci heaps is freely available on the web at the MIT Press website, as is all material that's removed from the algorithms book. So in some sense, it's even better because it's free now. But the reasons to remove it were, I think, along the lines of what Professor Tarjan said. Also, we know what people use and don't use, and it's not taught very much. So actually, it's a little off topic, but when you make, there are physical limits on producing books, and there actually is a page limit. Whereas if you went, if a book was slightly bigger, the pages would have to actually be twice as thick, and the size would actually double, and the price would actually double. So there are just physical reasons why one has to remove things. In terms of the question about AI, I think. We thought about this a lot. The fourth edition of Introduction to Algorithms has a chapter on machine learning algorithms, and we actually tried to write almost like a textbook on machine learning, and then threw it out because there are better ones, right? And you don't come to algorithms for that. So we tried to focus on the algorithmic insights that are in machine learning. So it covers now clustering and learning from experts and gradient descent, which are three of the most important algorithms. And another one that, I don't know how to put in an introductory book, but matrix multiplication, of course, is another important one, although beyond Strawson in an introductory text, I don't know how to cover that. And splay trees, we've thought about that. It's hard, I don't know, just, maybe we need you to write it up in a very concise way, but to try to digest it in a concise way. We sort of failed at that, actually.
One thing they did put in was the inverse Ackermann function analysis of union find, which previously was log star. And I've got a 3-page write-up, or maybe even 2-page write-up of this analysis, and I teach it to undergraduates. And after about the third time of seeing it, they understand it.
I still use log star n because it's easier to explain. Inverse Ackermann function is just something that beyond the first call, it seems to me. The first call and for algorithm call. Yes, that might well be true, but I also think from a mathematical point of view, it's an amazing thing. The fact that this bound comes from this crazy function that was invented for a completely different reason. So if you put this in some context, and the other important thing is that it introduces the idea of double induction, which I think is mysterious to students, but it's very important that they learn it. So I think there are pedagogical reasons to do inverse Ackermann function instead of log star, but
okay, yeah. I think fortunately we invited Cliff join the panel, right? Okay, so I think it's about time to end. Okay, so thank you everyone.